Hello everybody. Today I am going to discuss large dataset processing with Hadoop and MapReduce. In this session I am going to discuss these key points: problems with large dataset, Hadoop environment setup, MapReduce, MapReduce data flow, MapReduce application, then references. So what are the problems with large data set? So before going to the problems, I'm going to tell you about large data set. So in current scenario, the organizations are handling lots of data, and these lots of data are generated by user or internet, and there are various means like microblogging sites, blogging sites, and social media content. So there are lots of way and various sources which are generating lots of data, and there are lots of there are various type of data is also generated, like text, video, audio, and hybrid of all three. So dealing with lots of data, we face some challenge. So these are like storage and data processing. In storage, if we are handling terabyte data, we need lots of hard drive. Like for 100 terabyte data, we need 250 hard drives of 400 GB. And there would be a possibility that our one file cannot fit into one hard drive. So how can we solve this problem when we are handling large data set? So this is a major problem in storage. We can't avoid the number of hard drives or capacity. We cannot reduce that. But major problem is that the single file cannot fit sometimes in one hard drive. So the solution will be for this. It can be stored in a distributed fashion. So Hadoop provides distributed file system which can solve this problem. Hadoop can solve this problem with easily distributing the file into chunks or blocks and storing it into different machines in clusters. Another problem is data processing. So data processing, whenever we have lots of data, we want to play with that data and we want to extract the knowledge from that. We want intelligent information out of these data, so that we can get some benefit for our business. So, but there is a problem with the lots of data. If we want to read only, if suppose for example our computer can read only 30 to 35 MB per second from a disk, then if we want to read 100 terabyte data, it would take approx 1 month to read the data only. And we need to do obviously lots of data mining and other processing to get information. So we need some kind of framework or some kind of solutions which provide data processing faster. So Hadoop again answers this problem. We can do easy processing and faster processing. So I'm going to tell you about Hadoop now. Hadoop already won terabyte slot in 2008. Their Hadoop contributor already proved with 910 nodes. Each machine has 2 quad-core CPU, and with CPU speed 2 GHz and 8 GB RAM, with number of mappers 1800, and again reducer also 1800. They have solved the terabyte slot in 209 seconds. Yes, it's 209 seconds. So it's very fast. So we can also solve this problem. We can also play with the terabyte data and petabyte data, and we can solve it in few hours or few minutes. So what Hadoop provides? Hadoop provides highly scalable distributed computing framework, and it actually allows for distributed processing of large data set across a cluster of computers using a MapReduce programming model. So it means in Hadoop, we need to use MapReduce technique because MapReduce is the heart of Hadoop. So, but we don't need to bother about failures because it detects the failures and handle failure at application layer. Same, Hadoop provides high available service. What I mean about high available service is whenever some data node or some machine goes down, it automatically recovers the data in a cluster, and user or developer don't need to bother about that. And later on we can again add the failure machine or new machine in our cluster so that we can use that machine again. But we don't need to worry about data losses because we already in Hadoop we can configure about replication factor so that our data can be recovered, and every time name node always check about data is recovered or not, or data node is in cluster is present or not, by giving heartbeat and by polling the machines. So always keep a name node always track on the what is going on cluster. So what are the major components in Hadoop is data node, name node, secondary name node, job tracker, task tracker, balancer. So data node is in our cluster is it is the machine which is actually store our data in a file system. Name node actually manages metadata about all cluster and cluster details and data nodes so that it coordinates storage and retrieval of individual data block managed by data nodes. Secondary name node is just backup of name node data so that whenever the name node goes down or fail, it can recover by secondary name node information. So our cluster basically made of name node and data node. So mostly we have one name node and multiple data node. So it's like a master, and master is a name node and slaves are data node. Another thing is job tracker. Job tracker and task tracker is usually comes when we need to process some data or we need to run some operation or processing on Hadoop cluster. So same way as name node was master, here job tracker is act as a master and task tracker act as a slaves. Whenever we submit any job to job tracker for processing, then it divides the job into tasks, and that each task is distributed to available task trackers. And each task tracker processes assigned task and generate the output and submit that information to job tracker. Job tracker always polls the task tracker, is it available or not, and is it working or not. So whenever some task tracker goes down between the processing, it reschedules the task to another available task tracker. Or sometimes it happens like task tracker could not process the task. So at that time, the failed task again can be restarted on the same task tracker or different task tracker also. So these information kept by job tracker by polling the task tracker, and it manages the job and resources in cluster. There is one more thing, balancer. Balancer actually balances the cluster. What I mean by balancing the cluster is, let's suppose we have 10 data nodes and one name node, and our cluster now almost 80% full. So we are and data is generated day by day, data is growing. So how we can handle that data and how we can fit that data in our cluster. So we are unable to fit that data into cluster. So that time we need to add more data nodes to our cluster. So if we add new data node, so they have more spaces, and other data node has, the previous data node has less space available. So balancer balance the data across the cluster so that all data nodes can have around equal spaces left on these machines, so that other tasks can be done easily and storage can be increased. So we can, in Hadoop, we can actually increase the storage whenever we need it. Or if we want to reduce the size of cluster, we can easily reduce that, and we can remove one by one node, and balancer will balance the data across the cluster. So I'm going to show now how we can set the Hadoop environment on our machine. So before that, I'm going to tell you, you need Java installation on your machine and Hadoop directory from internet. You can download Hadoop directory and you can extract on machine. Then you can proceed like this. Yeah. So here in this, I'm just making a sample cluster for 2 machines. In this cluster, we have 2 data nodes and 1 name node, and 1 machine is name node also and data node also. So we have conf directory in this. We need to set up core-site.xml. Here we can set all properties, like there are lots of properties here, and few are very important. Like I'm just telling you about the important one. This property is fs.default.name. Here we need to mention our name node IP. Whatever your name, whatever the machine you want to make it as a name node, you need to give IP of that name node. Another property is fs.trash interval. It's needed when you delete something from your cluster. It will, how much time it will remain. So it enables the interval for trash checkpoints, number of minutes between trash checkpoints. Other properties are like, you can set temporary directory. Here I'm just setting the as it is. I'm giving the, because my user is root, so I'm providing the root here. So another property configuration file is sdfs site.xml. In this you need to provide the DFS path. Here this is a important property, DFS dot replication and interval. So I set it to 3. So it's a, this is a periodicity in seconds with which the name node computes the application work for data nodes. It means our data can be replicated after 3 seconds. So Same way you can set the heartbeat interval, which is a polling to the data node. This is a replication factor which I am talking about. It is useful when we want to recover the data. So it's a 3 here. So we can recover whenever the data node lost, we can easily recover the data because the balancer will balance the replication after 3 seconds it started whenever it goes down. Same way, the DFS directory where our name node information will kept, it's the path of that dfs.name directory. So the temporary directory, whatever we set, and /dfs/name. There are other few properties you can also set. These port number you can change or you can set as it is. After setting these, you need to set MapReduce site.xml. Here you need to mention how many maps and how many reduced tasks are there. There are other properties which are it comes with the default file. You can keep it as it is or you can change also. So this is the property. How many maps are there? So I set here 5 because we have 2 machines and these are 2 core machine, dual core machine. So I'm just setting 5. And here the reducer, number of reducer, I'm just setting 2 because we have 2 machines. We can actually set more also, but I'm just taking a sample here. Another things are like slaves. So I have 2 machines in my cluster. So these IPs are I've given. These 2 machines will act as a slave, means it will act as a data node and task tracker as well. Same here, master. So this is my master node, means it's a name node and job tracker node. So I'm going to show you some more commands with the Hadoop. So everything is set now. So if you want to start a cluster, I'm already having cluster started, so I'm just stopping the cluster. So from there, so I want to start my cluster now. So I need to give this command start dfs .sh. This started our name node and data node in cluster, then secondary name node. We can check this on our browser. So here we can check the DFS health, means cluster health. So it's showing that it's in safe, that there is a safe mode is on. So it's taking it some time to on our cluster. It would go after a few seconds, like I'm going to refresh it. Now it disappears. So it's showing that what are the configuration capacity in our cluster, DFS used, non-DFS. So all the information about our DFS cluster. So, and we have live nodes too, because I have added only 2 nodes. So it's showing 2 nodes. There is no dead node. If something has failed, it would show in dead nodes. So we can check here live nodes. So it's showing, I kept the name one data node master, Hadoop master, and another server name. So these 2 machines in our cluster, and how much data is already on this cluster, on this machine, it's showing that. So after the cluster has been started, we need to start job tracker on the same machine. So for starting a MapReduce, or you can say job tracker and task tracker, we need to start bin/start mapred.sh. So it eventually starts job tracker, then task trackers on data node. Job tracker we can start anywhere, on any machine. There is no necessity on, we can start on name node only, but here in example I'm just starting on name node machine only. So I need to check is it working or not. So this is a port, it's saying our job tracker is on. We have 2 nodes, these are the nodes, these are the data nodes, and these are the task tracker machines now. And it's also showing the heartbeat interval. So you can see the number of map tasks, reduce tasks, failure, and everything you can see here, because it reports and it monitors. That is the main functionality. So after setting up Hadoop, we can go to the MapReduce task, because we need to run any MapReduce task on this cluster now. So we are, I'm taking the MapReduce. What is a MapReduce now? MapReduce is a simple programming model which is designed to compute large volumes of data in parallel fashion, and because it divides the work into set of independent tasks. So what I mean, MapReduce, whenever we have data, we need to convert data into key and value pair, and we can actually split the input and give it to different data node or different machines to process the data. They execute their input and produces output, intermediate output. After map has done, the reducer will come. So these intermediate data or result goes to reducer, and then reducer collects and aggregates the data and produces the final output. MapReduce provides automatic parallelization and distribution. So we don't need to worry about which task will go on which machine. Job tracker automatically divides, and it automatically assigns that task to available task tracker. We don't need to actually worry about. We need to focus on application and logic. Another thing is fault tolerance. So fault tolerance also it provides, because whenever there's some data node goes down, it automatically recovers the data, and you don't need to worry about it again. Input output scheduling, the same way, whenever something has been failed or machine goes down, it reschedules the task onto another available task tracker. So it also provides this input output scheduling. Another thing, monitoring and status updates. So that I showed in browser right now, in previous slide. So we can see what are happening in our cluster, what are happening with the task or job. So we can monitor that. So it provides a great framework and we can design our algorithm into MapReduce style. It's a functional construct. We need to take care about only how the data will be goes into map function and reduce function, how it will be flow in our algorithm, and how it will process so that we can achieve high degree of parallelization, and we can actually process good amount of data in optimal time. So MapReduce, I already explained about this. So in MapReduce we have two functions, map function and reduce function, and map also takes input data in key and value format. So list of data elements are provided to mapper function, which is called a map function, which transfer input data to intermediate output data element. After map, there is a combiner, which is a mini reducer, which combines the key, aggregate the key, then it copies to reducer, and then sort it, and then reducer will play the role, and reducer will play with the intermediate output and generated the final output. So reducer function receive an iterator of input value from input list, then it combines these values together, then returning a single output value. So I'm going to show this with one example, word count problem. So I'm going to show the code first. So this is a word count class. In this we have map function. This is a map function. Then another thing is we have reducer function. And there is one basic thing which is start MapReduce, this main function. Here we are making a configuration. So jobconf, with jobconf we are setting some configuration, we are overriding some configuration. So here we are giving like which format we want for key and which format we want for value, because in output we have key and value. So we are just taking tag which class should be there and which value should be there. So here I am setting text.class, here I am setting iterable class. Why I am setting this before? Because our problem is word count problem, and in this we have lots of data. We have big file or multiple files of big size. Now we want the word and their occurrences across the all documents, all files. So my final output will be like word, tab separated, then frequency of that word across the all document. So here I am setting the output class. So that's why I set the text, then iterable. Then we have to define which mapper should be used. So it's a map.class, and combiner is again reducer, reduce.class, and reducer is also reduce.class. I'm going to explain these all. So another thing is input format. We are setting here input format. So which format we are taking input and in which format we are going to output our output. So this is a text input format, and the output format is text output format. So there are various kind of input format like text input format and sequence input format and key value input format. So we can take here it's a text input format is suitable because we want to read a file. So text input format provides key and value. In key, byte set of file will be there, and in value the text will be there. So text will be line, so line will be there. So in text output format it will return, so our key will be text as we define here, text as output key class, and int iterable, so it would be the frequency or integer value in text output format. So it would be the key and value will be tab separated in text output format. So there are other format like null output format and sequence output format. So it depends when we need which one. So after that, here again I have set the one more configuration thing. So it from where we need to read the input and from where the output will comes. And finally after that we need to submit the job, this configuration to the job, so that our driver process will run and it will call map and reduce. So this map.class and reduce class, having the map class has map method and reduce class has reduce method. Like this is the reduce class which has reduced method, and here it is a map class which has map method. So in this, just the key and value are there. So in key we are getting byte set, and in value we are getting lines from the file. So in this statement it's just taking the line and it converting into tokens. Then tokens are set here, and with each word we are just collecting the word comma int iterable 1. So for each word just we are collecting the word comma 1 kind of tuple, and after that when the map function goes over, so then all keys will be combined with the combiner. So in our case here combiner is reduced class only. So in reduce class we have reduced method which actually iterate on the values, like there are words so which have which has word comma 1, word comma 1, word comma 1 multiple times. So it combines the value here. So if there are 3 occurrences, it will collect as a word comma 3 or whatever the count will be. So I'm going to show the how it will execute. Okay. So I'm taking a big file. So this is a input sample in my cluster. So this file is actually 700 MB. This folder actually contains 700 MB files. It has multiple files in here. So there are lots of files here. You can see that. So across the all files, we need word count. So I'm going to run now. .run. Okay. So I'm running this, and we can actually monitor from the console, sorry, from browser. So here we have job tracker. So it's showing now running job is this one, which has word count problem. It tells about what job ID is there, and we can actually check on this console. It's running. It shows which user is there, which program is there, what are the status it's running now, and you can see here it shows about map and reduce. So how much percentage of map is completed, and there are 30 map it has launched and 2 reducer. You can see the data information also here. How many records are processed, how many records are going to as a map input, and how are going to combine, how many have been done. So here in graph also you can see that this is map completion graph. So it tells about 0 to 30 maps which it has been launched. It's going process, and here you can see reduce phase. So reduce has actually copy, sort, and then reduce. So copy has been started because some of map has been completed, so its copy has been started. Because we have 2 reducer only, so it's showing only 2 bars. If I'm going to refresh it, it is all done successful. It has taken 1 minute 36 seconds, and it's completed. And you can see that the copy, sort, and reduce actually done. Everything has been done. It also shows the failed or killed task attempts. So here no failed process, here no failed reducer and reduce killed, but there is some killed attempts. So you can see here, and these 2 tasks are killed, but they are rescheduled on another machine, and it has been completed. So that with our all job is not failed, and it has been, because of re-execution, it has been scheduled on another machine, other task trackers. So it has been completed now, and it took 1 minute 36 seconds for 700 MB file, and it can take actually less than that, because we have only 2 machines in our cluster, and these 2 machines are slow machines. So that is why with the configuration wise also it's not so good. So we can, if we have better configuration file, better configuration machine, then it can process these files and within few seconds. Now I am going to show you again slides. So we were talking about MapReduce. So how the data has been flowed. So in this process, there are various map tasks has been launched. Like in the previous browser, we have seen 30 map tasks were there. So there you can see that there are multiple map tasks, and each having the same map function, which I have showed in word count problem, and it's generating key value pair. And after that, it's partitioning. There is a partitioning function in our program. In word count, we actually don't need. We just need a combiner so that aggregate the values according to keys. So same keys will go on the same reducer. And after that, after copying, it sort the keys, and then after that it applies to reducer and generated the output. So yeah, you want to see the output. So what after processing, word count problem will give the results, and you can see that result. So we have created this file. This output has been generated. And we can read it because it's a text file. I'm going to cat it. So it's showing each word with the frequency. there are some chunk characters, so we haven't cleaned up. It's a sample program, so we haven't cleaned up. So you can see all the, for each different token or word, it's showing the occurrences, and these are key separate, text separated. So with the MapReduce app, we can do lots of application are there, and few are I'm showing in the slide. Like you can make inverted index, you can do document clustering, Vebling graph reversal, statistical machine translation, and machine learning, and other data mining process you can easily handle with the MapReduce algorithms, because these all problems has more data, lots of data, and we need intelligent information, and we can process it fast so that we can use it in another applications. So I'm again in one of them, one application I'm going to show you, like inverted index construction. I'm going to show you here. So it's a text indexer. It's just indexing the text. So I'm going to pass input documents. That document contains only a few lines, because for example I'm just taking this few lines, and it will make an index out of them. So there is a map function. Again, in our mapper class, text index mapper, we have map function, and the reducer class, text index reducer, we have reduced function. And in main function, we have configured few things. Like here, just I've set the output key value class, which I need in text format, and again value should be also in text format. I'm returning because I'm just providing the inverted index in terms of term as a key and value as a document file name. So we have set the output key class and output value class. After that, we have added the input path and output path. After that, we have set the mapper class and reducer class, and then we are submitting the job for run. So in map class, it's a long writable key and text is value. So again, it is giving the file, and file we are splitting here. As it is the same program as a word count program, but instead of counting a word, we are just taking the name of the file, and we are with each word we are just throwing the file name. So like here, word and the file name. So in file name, I'm storing in location. Location is text class object, and in location we are setting the file name, and file name we are processing with the file split object, and file split object is made up of with the help of reporters get input split function, which always tells about the file, metadata about file. So we can get the name of the file from here and then set it. Then we are again tokenizing with each word, we are collecting the file name. So after that, once we collect the word comma file name, it will again goes to combiner. So combiner, we have not set here combiner, so it will directly go to the reducer. So in reducer, so we are going to do same thing as we are in word count problem. We were summing up all the occurrence coming with the word. So here, instead of summing up, we are just appending the file name, different file names. So here just we are appending in this to return, which is a string builder object. We are just appending the values of whatever the file names are coming, whatever the locations are coming, which we are adding here. And this logic is actually just doing making the comma separated file name. So, and after that the final output will give word comma whatever files are there, means all files which contains this word will be the output collected by output collector. So it will create our index. I'm going to show you how you will run here. So first this program is I'm going to compile. So I'm going to run it. So because our input was very small, it ran very fast. I have these files in input. I've given only 3 files in input, which has these things. One or two lines. First, document A has Times of India, document B has economics times, number of times, and document C has time jobs. So now what the output has came now. So it would be, I'm doing the cat here. So our output is like term and the document where it present. So in the economic was present in document B, so it is there. So it's like an inverted index, the term and document, related document. So for times it appears in the 3 places. So it is giving this document A, document B, and document B again. It's a sample program, so we can actually solve. We don't need 2 times. So I'm going to show you one slide. So in actual application, we need a positional index, and the positional index also can be created very easily because I have showed a word count problem and inverted index problem. So we can combine these two, because in this in positional index we need occurrences. Like here you can see there is a term as a key and the value as a pair of document ID, term frequency, and term positions. So here, like Times of India has been split into 2 tokens, Times and India, of a stop word. So we have removed it. So first this is a Times is a key and value has document ID A, then term frequency 1 because it appears only one time, then term position, it appears only on first position, so it's first only. Same for India. India has a it appeared on document A here, and it has comes again 2 times, so it's a term frequency is 2, and then positions is 2 and 3. It's not keeping count off, so it is skipping that. After that, document B, again same thing. You can see the same as for same for document C also. So multiple maps are running and generating this kind of data, key and value pairs, and these key value pairs are applied to shuffle and sort so that it aggregates the key, like it and the same key will go to the same reducer. So times is it can aggregate the times and it can go to the same reducer. Another key can be split into another things. And the final output of the reducer will be the index, which has term and this tuple, document ID, term frequency, and term positions. And it will look like key value. So key will be times and value will be first. So value will be sorted by document ID. So here document ID A is ahead of B. It's sorted A and B. Then it has all value like how many times occurs in A is 1, how many times it occurs in B is 2, and position in A is 1, position in B is 2 and 4. Same way for all. So that it actually, this index actually helps for faster retrieval in index searching application. So this kind of application we can actually use with the MapReduce, and there are other applications as I told. So there are lots of data mining and machine learning applications are there which can be easily do with the MapReduce. And there are lots of things like social media content we can process through we can calculate the recommendation system in social media, like friend recommendation in Facebook. So these all applications and very there are very much in demand nowadays. So we can do it with the MapReduce technology. And MapReduce, at the conclusion, MapReduce is actually provides high degree of parallelism that can be achieved by application. It can provide high degree of fault tolerance, and because it uses with the Hadoop, and these Hadoop thing is actually gives the framework to use MapReduce optimizely. So, and Hadoop is open source and its major contributor is Yahoo, and there are lots of Hadoop users in our internet space. These are Facebook, Google, IBM, Amazon, Reddit, and Yahoo itself. So, and there are lots of startup and other people which are using nowadays Hadoop, because the Hadoop is a requirement for handling lots of data. It provides a good solution to handle the data, and because it stores data in SDFS, which is Hadoop distributed file system, and actually at core logic is MapReduce, which with MapReduce we can process the data and we can get the intelligent information. And eventually the Hadoop, some people confuse with the, so we can use in place of database. So I'm going to tell you them we cannot substitute database in place of, in Hadoop cannot be used directly in place of database. And same thing, Hadoop cannot be, Hadoop is not replacement of RAID controller, RAID devices. Like people confuse with that because it provides high available service. So can be used RAID instead of RAID or SAN, storage area network device disk, we can use Hadoop. So it's not the thing we can use with that. It's not a replacement of SAN or RAID controller. It just provides the high available service because it maintains the data replication, and it balances the data in cluster. If data node goes down, we cannot recover easily. It cannot recover easily automatically. Then manual intervention will be there, but data will not be lost, and a user or developer cannot we worry about. We don't need to worry about what is happening with our data. So because data will be kept secure. So I'm going to end this session right here. So these are the references. You can go with these references to know more about Hadoop and MapReduce. Thank you. Thank you, everybody. Any questions?